Hello everyone, this is your tutor AB, and today we're going to be looking at one of the questions from the May 2021 Paper 1 HL.IB Physics examinations. This is a question about a mass moving down an inclined plane. So let's solve this together. A mass is released from the top of a smooth ramp of height h. After leaving the ramp, the mass slides on a rough horizontal surface. The mass comes to a rest in a distance d. What is the coefficient of dynamic friction between the mass and the horizontal surface? Okay, it's an interesting question, so let's see how to solve this. Well, they're asking for the coefficient of dynamic friction. So the formula for dynamic friction is F of F is equal to the coefficient multiplied into the normal force. So if we rearrange this formula, we get F of F by N gives us the coefficient that we're looking for. So this is the formula that we want to use at the end to get our answer. But how do we get that? First, we need to find out what is the frictional force. We already know the normal force. Normal force is simply just the mass into gravity while it's moving down here. But I'll come back to that later. So we need to find the force that's acting on the mass while it's traveling from this position to this position. What is the force that acts upon it that makes it go from a velocity to 0 meters per second? What is that force? That is our frictional force, and that is what we want to find. Before we can find it, we need to find what is this velocity. This velocity is the final velocity after coming down the ramp and the initial velocity when traveling on this horizontal surface. So let's find this velocity, shall we? In this question, do we have time? No. So we need to use one of our timeless kinematic equations. We have v squared is equal to u squared plus 2as. We can use this equation. So we need to find v squared and then make it v. So how do we do this? V squared is equal to u squared has to be 0 because initially it's not going to be moving, so 0 plus 2 into the acceleration. Now I want to make you, this is a tip, this is a important note. The acceleration of a mass down a frictionless ramp can be represented by the equation ma is equal to mg sine theta. This always works down a frictionless ramp. So acceleration is g sine theta. This works for all objects down a frictionless slope. So for A, we substitute in g sine theta. And of course, we know that this block is suspended at some angle. It's coming from some angle, and that has to be theta. So what is this displacement right here? That is what we need for our equation. So let's find it, shall we? To find S, which is what we want, we need to say sine theta, which is our trigonometric ratio, is equal to h, which is the opposite length, over the hypotenuse, which is s, which is what we want to find. So when we rearrange, we get that s is equal to h over sine theta. So we can substitute this directly into our equation. So v squared is equal to 0 doesn't matter, so 2g sine theta multiplied into h over sine theta. Sine theta get cancelled, so the velocity squared is equal to 2gh. So the velocity at this final point of the ramp is equal to the root of 2gh. This is important, so let's make sure it can be seen. So let's update our diagram with this velocity that we just found out right now. Root of 2gh. So now that we find this final velocity, we need to find the acceleration that occurs from this point to this point. What is the acceleration that has happened that led it to go from this velocity of root of 2gh to rest 0 meters per second? With that, we can then find the force. So let's find the acceleration first. Acceleration can be found again using the kinematic equation, which is v squared is equal to u squared plus 2as. Because we don't have time, so we must use it again. Our v squared this time is 0 because the object is now finally at rest. So 0 squared is just 0, is equal to the velocity, the initial velocity, which is root of 2gh whole square, which is our formula, root of 2gh whole square, which is the initial velocity. The final velocity down the ramp is the initial velocity down this horizontal, plus 2 into acceleration, which is what we want to find, into the displacement, which they've given us the variable d. So we just use the same variable, d. So let's solve for the acceleration. So when we solve for the acceleration, we get 0 is equal to 2gh, the root and the square root cancel out, plus 2ad. So let's bring 2gh to the other side and solve for a. Negative 2gh, the sign changes, is equal to, and what I want you guys to understand is that there is a deceleration that occurs from this point right here to this point. So the acceleration is actually negative. So we can denote that in the variable 2 multiplied into negative a into d. This just ensures our sign at the end is correct. So let's rearrange. As it's a negative acceleration, we can just say negative a. So negative 2gh by 2d is equal to negative a. The negative signs can cancel, and so this is our acceleration. 2 and 2 will also cancel. So our acceleration is gh by d. That is our acceleration. Now we want to find the force that occurs, the force that acts on this mass while it's traveling this distance of d. What is the frictional force? So that can be represented by the equation F is equal to ma, the simple equation. We know the acceleration from the working out previously, so why not just substitute that in? F is equal to m stays the same, we don't know the mass, we're working with variables here, g h over d. Now that is our frictional force that's acting on our object while it's traveling. That is this arrow right here. That is the frictional force that's causing it to slow down. So now that we found this force, let's look back. We said all the way at the top that the coefficient of dynamic friction is equal to the frictional force by the normal force. Now, the normal force in our case is just going to be mg. The reason for this can be explained by this diagram. This is our object. It has some weight downwards, mg, and the floor puts some weight back, puts some force back on the object such that it does not go through the ground, and this is equal in magnitude, and so the force that's acting upwards, the normal force, has to be the same, mg again, and therefore the normal force is mg. So let's put this all into our equation that we identified at the beginning. We said that f of f by normal force is equal to the coefficient of dynamic friction, which is what we want, isn't it? So we can substitute everything inside. mgh over d by the normal force mg, which again gives us mgh over d multiplied into 1 over mg. mg and mg get cancelled, and so finally our answer for dynamic friction comes to be h over d. And so let's double check, is this an answer that can be seen? These were the 4 options for this question, and yes, our answer is there. It's option D, and so we've solved this question.